Good morning, welcome to new lecture. Today I will start new topic and I will talk about twist angle and shear stress due to torsion or torque. Assume we have one shaft and this shaft cross-sectional area is circular shape. So we have one shaft, cross-sectional area is circular. So if I show the cross-sectional area, is like this, and assume this is solid shaft. This is solid shaft. If we have one point here at center, for example, point A, and this is side view. Here this point A at cross section will be here and O will be the center of the cross section. This is solid shaft with circular cross section similar to this what we have here. We clamp to the wall, so here it is fixed support, and at the end I apply one torque or twisting moment. So if I apply one torque twisting moment, and this is, you see, point A location, we have this shaft, and here at my hand we clamp this and I apply torque here. If I apply torque, you see what will happen. If I apply torque here, point A, initially at point A, will come to another location like A prime. So, if this is initial line, this line location after we apply straight line, it is horizontal initially. Then after we apply torque, because point A will transfer to point A prime, this line will deform like this. And this angle I show with gamma. If you remember, we have shear strain. In shear strain, if we had one block and I apply force here, like this, then it will deform like this. And we call this angle shear strain, and we showed with gamma. So again the same gamma, and gamma here, it was equal, if you remember, this deformation delta divided by this length L. It is same gamma. So here after deformation I can write gamma is equal to AA prime divided by L length in this triangle. Gamma is a small number, so tangent gamma is equal to the gamma is equal to AA prime divided by L. So from here I can write A prime is equal to gamma times F. If we look at the cross section, after we apply torque, T cross section, this point A, it comes here, A prime, and this angle I show with phi, we call it twist angle. So we call that twist angle phi. Now here in this triangle, if phi is small, I can write A prime in this triangle is equal to phi times from center to outer surface. If radius is r, it will be equal to the arc. So I can write A prime, this arc is equal to radius times phi. Phi is twist angle and gamma is shear strain. From here I can write gamma is equal gamma times L is equal to phi times R. And you see, once we come from point O center to the outer surface, point A, this AA prime is the maximum value. So if we look at to another fiber, for example, it moves from here to here, this is smaller. So here AA prime is maximum value and gamma shear strain for outer surface will be maximum value. So I can show with gamma max. From here, gamma max will be equal to twist angle phi times R radius divided by L length. Let's see what is happening in this cross section. If we look at the cross section one more time, this is point O, this is initial location of the point A, this is a straight line. If we apply torque, observation shows this point will transfer to point A prime and we will have deformation from A to the A prime. If we assume another point here is B, that point B will transfer here point B prime. If entire radius is capital R and from center to point B I show with lowercase r. What is happening here? Due to this torque, we have this torque will produce stress in cross-section area. That stress is shear stress because it is tangent to the surface. Because we have here maximum deformation, the maximum value of the shear stress will be here, tau max. And because point O, center point, deformation is 0 in lateral direction, there shear stress will be 0. So if I draw the shear stress distribution, the distribution of the shear stress will be like this. Here it has a maximum value, at center it is 0, and from center to outer surface, linearly it gets bigger. It gets bigger. Now we know that if I assume one small element, here, for example, shear stress in this small element, assume it is tau. Shear stress at outer surface, it is tau max. And we can draw this triangle. Look at here, in this triangle, tau, this small element up to center, if I show with lowercase r, and entire radius with uppercase r, from similar triangle I can write tau over tau max is equal to lowercase r divided by capital R. From here I can write tau is equal to r over capital R times tau max. And you see R is function, tau here is function of the location, function of R. So force times stress, tau, times area of that element, stress, tau, times the area of that small element, dA, will give us force, dF. dF, force here, times this R, times the distance from this element up to centroid. It will create us moment, torque. So dt will be dF times R. From here I can write, instead of df, tau dA times r. Because tau is function of the r, I can plug instead of tau from here. So I can write, instead of tau, I can write tau max r divided by capital R times dA times R. If I remove this picture here, I'll write that one more time. I can write dt is equal to, finally, tau max lowercase r capital R dA times lowercase r. If I integrate this, I will end up with total torque. If I integrate means if I sum the moment of each small element, summation on that surface means integration over that surface. If I integrate that, integration of tau max over r times lowercase r squared dA. Pay attention, this tau max over r, it is constant. Constant number you can pull out of integration, so it will be tau max divided by radius of the shaft, integration of r squared dA. This term, integration of r squared dA, you know from static, if you refresh your memory, come back to the static, you will see integration of r squared dA was polar moment of inertia. It was polar moment of inertia, and we used to show that with J. If you remember from static, J, polar moment of inertia was integration r squared dA. So instead of this, I can plug J. If I plug J instead of that, I will end up with what? T is equal to tau max divided by R times J. T, torque or twisting moment, is equal to tau max, maximum shear stress, which take place in outer surface, divided by R, radius of the shaft, times J, polar moment of inertia of that section. I can write this in another form. I can write that like this. I can write that tau max is equal to torque times radius r divided by J, polar moment of inertia. If here we plug capital R, means entire radius for shaft, we will find tau max, maximum shear stress, which take place in outer surface. So for any fiber in lowercase r distance from center O, I can write tau shear stress is equal to T torque times the distance up to center point O divided by polar moment of inertia J. So if for one shaft I have the radius, I can calculate J, polar moment of inertia. If it is solid shaft, polar moment of inertia for circular solid shaft, it is pi r squared over 4. I can prove that it is, r, not square, r to the power of 4 over 4. So for one solid shaft, it is solid shaft, the cross-sectional area, it is circular. If I have radius r, pi r to the power of 4 divided by 4 will be polar moment of inertia. So that is known value. For one solid shaft, if I have the radius, I can calculate J, polar moment of inertia. Then, if I apply torque T, T is known value, the maximum shear stress will take place in outer surface, and the magnitude, it is tau max. The magnitude is tau max. At center is 0. From center to outer surface, linearly will increase. Tau max I can find with this formula, T times R over J. On the other hand, from Hooke's law, we know tau is equal to G, yeah, shear modulus times gamma shear strain. So for tau max, this will be G times gamma max. We know gamma max is here. Gamma max I can plug from here, G times gamma max, it is phi twist angle times radius divided by L. So let's see what is happening here. Tau max is equal to G times gamma max. Instead of gamma max I plug this, I will have this term, so I can write tau max is equal to G phi R over L, shear modulus times twist angle times radius over L. On the other hand, tau max is equal T R over J. If we put these two equals, I can write T R over J from here. This is equal to the tau max, this is equal to the tau max. If I put equal, I will end up with T R over J is equal to G phi R over L. From here, R and R, they will cancel from both sides, so phi twist angle will be equal to TL over GJ. Twist angle in one shaft is equal to, please pay attention, shaft here has circular cross section. Twist angle is equal to T, torque, times L, length, divided by G. G is shear modulus times J, polar moment of inertia. From here, I can write T over phi. T over phi is equal to GJ over L. T over phi is equal to GJ over L. What is GJ over L? We will call it torsional stiffness. Let's come back to our topic. If we compare these now, if we have one shaft with circular cross section subjected to tension or compression like P, again the same shaft subjected to torque T, see what is happening. If we apply axial force, deformation delta will be PL over EA. Stress will be normal stress, sigma is equal to E epsilon, or sigma is equal to axial force P divided by A, cross-sectional area. And axial stiffness was K is equal to EA over L. So axial force will cause axial deformation. Magnitude is equal to PL over EA. Stress will be P force divided by A, and it is normal stress. Normal stress means if we cut it, it is perpendicular to cross-sectional area like this, sigma. And axial stiffness or axial rigidity, it is EA over L. If we have the same shaft, we apply torque T. Instead of axial deformation, we will have twist angle. So this is cross-section. Point A here will transfer to point A prime. Twist angle phi will be equal to T L over G J. You see what is the difference? Axial deformation, twist angle. Axial force, torque. Length. Young modulus, shear modulus. Cross-sectional area, polar moment of inertia. Instead of normal stress, we will have shear stress, which is equal T torque times radius over J. And torsional stiffness, K and this theta will be equal to G J over L. You can compare and see what is the difference. If we have solid shaft, polar moment of inertia, we can prove it using integration, and then we can memorize the result. It will be pi r to the power of 4 over 2 if we have solid shaft. If it is hollow shaft, instead of solid, the outer radius, for example, it is R1, the inner one, it is R2. This will be polar moment of inertia will be pi R1 to the power of 4 minus R2 to the power of 4 divided by 2. So you see how we can modify for hollow shaft. Now, if we come back to look at to that shaft again, if we come back and look at to that shaft again, I apply torque T here, and because of T, cross-sectional area, we will have shear stress. The shear stress will grow from 0 to the maximum value linearly, tau. If I assume one element here, this side of the element I have this tau. That element here, this is tau max. So that will create another shear stress in this direction, tau max. In order to have equilibrium in this element, I will need these shear stress as well, tau max and tau max. In other words, the shear stress that act in the surface, in the axial surface, will create shear stress in the longitudinal direction. If I cut this like this, and I show that part if I cut a shaft in longitudinal direction, from inner to the outer, shear stress will grow like this. And this shear stress will produce shear stress in this direction as well. And from outer surface it comes to inner, it gets smaller and smaller. And in other side it will be in inverse direction. As a result, if we apply torque to the shaft, we will have shear stress in any section. If we cut perpendicular to the shaft, we call it axial surface, we will have shear stress, and shear stress distribution is linear. At the center point it is 0. From center, if we increase the radius, it will increase. Those shear stress will produce shear stress in longitudinal direction. Again, distribution of these linearly will increase. Close to the center it is 0, and from 0 if we increase the radius it will increase. And this is right, this kind of shear stress distribution, it is right for shaft with circular cross-sectional area. If shaft cross-sectional area it is not circular, we should modify that. Later on I will talk about that, but all formulation, that twist angle, I prove it, or that shear stress distribution, it is right for shaft with circular cross-sectional area. Shaft with circular cross-sectional area, because it is axisymmetric, so we will not have distortion in cross-sectional area. If it is in another shape, for example, a square shape, or it is rectangular shape, that assumption, it is not valid anymore. So if we apply torque to one shaft, cross-sectional area, it is not circular shape, it is, for example, a square shape. The plane after deformation will not remain plane, and we will have distortion in those surface. So if we have shaft with circular cross-sectional area, all plane perpendicular to this shaft, before deformation they are plane and perpendicular to the shaft. After deformation they will remain plane, again perpendicular to the shaft, and we will not have distortion. But if it is in another shape, we will have distortion. So if I write that here, because it is important, I would like to write on the board for circular shaft, I can write every cross-section of a circular shaft will remain or remains plane and undistorted. Because a circular shaft is axisymmetric. This is right for shaft with circular cross section. That can be hollow shaft or solid shaft, no problem. But if the shaft cross-sectional area, it is another shape, like diamond shape or square shape or rectangular shape, this assumption is not right, so those formula, I prove it, it is not right anymore. Of course, we will look at those one by one later on. Let's see, I cover everything. So, I summarize everything. If we have shaft cross-sectional area is circular shape, if it is solid or hollow, no problem, and it is subjected to the torque T. In that case, the stress we will have in each cross-section, it is shear stress. Those shear stress, we have those shear stress in axial surface. Axial surface means we cut these perpendicular to the rod and it is like one circular. The distribution of shear stress is linear. It is zero at middle and it comes to the maximum value in outer surface. Distribution is linear. Magnitude, we can calculate torque times the radius, the distance of that fiber up to center divided by J, polar moment of inertia. Polar moment of inertia for circular shaft is equal to pi r to the power of 4 divided by 2. We know that. Twist angle phi, twist angle means in axial surface. This angle phi. Point A comes to point A prime because of this torque. Twist angle is equal to TL over GJ. G is shear modulus, and if you remember, for isotropic homogeneous material, G is equal to E Young modulus divided by 2 times 1 plus nu. Nu was Poisson ratio. Poisson ratio is equal to negative ratio of lateral strain divided by axial strain. So if we apply torque, we will have shear stress in axial surface. Those shear stress will produce shear stress in longitudinal direction. So again, if we cut this shaft in longitudinal direction, like this, in this surface we will have shear stress to. Why? Because if we assume one element here in outer surface, for example, this element here, it has one tau max. That tau max will produce another shear stress here, tau max again. Now this element, it is not in equilibrium, it can rotate. In order to have equilibrium, we will need shear stress in longitudinal direction. These will be equal to, and in opposite direction, and they will be equal to tau max 2. So shear stress in one surface will produce another shear stress in perpendicular direction to that surface. Shear stress in this plane will produce shear stress in another plane which is perpendicular to this plane. You see that. So we will have shear stress in longitudinal direction as well. If we compare this with what we had in the axial deformation, in axial deformation, if we have a shaft subjected to axial force, deformation is equal to P times L divided by EA. Hooke's law here It says sigma normal stress are perpendicular to the surface, E times epsilon. We can calculate normal stress, axial force divided by cross-sectional area. Young modulus here it is E, and axial strain epsilon, axial stress is sigma, axial stiffness is equal to EA over L. If we have the same shaft subjected to the torque, deformation will be twist angle. It will be torque times length over GJ. Hooke's law here says tau is equal to shear modulus times gamma shear strain. Shear stress we can find with TR over J. J is polar moment of inertia, it is pi r to the power of 4 over 2. Rotational stiffness is equal to GJ over L. Stress due to axial force, it is normal stress sigma. It means it is perpendicular to the axial surface. Stress due to the torque, it is shear stress. It means they are tangent to the axial surface. So pay attention to this. I think for today it is enough. See you next session. So bye bye.